Hi everyone, good afternoon. My name is Dr. Munirathna, Assistant Professor, GFGC, Koteshwara, Kundapura. See, in this session number 14, it is mainly related to diffraction, Fraunhofer diffraction at double slit and its condition. From this concept, we are mainly focusing on interference maxima and minima, diffraction maxima and minima, and how intensity is distributed throughout this spectrum. Let AB and CD are the two rectangular slits parallel to one another and perpendicular to the plane of the paper, and A is the width, the B is the width of the opaque portion, and L is a convex lens, MN is a screen perpendicular to the plane of the paper. Then P is on the screen such that OP is perpendicular to the screen. Let A is the plane wavefront. From this case, all the secondary waves traveling in a direction parallel to OP come to focus at P. Therefore, P corresponds to the maximum position of central bright fringes. So this is the figure related to this Fraunhofer diffraction at double slit. In this case, the diffraction pattern has to be considered in two parts: interference phenomena due to the secondary waves from the corresponding points of the two slits, and diffraction pattern due to the secondary waves from the two slits individually. For calculating the position of interference maxima and minima, theta is the angle and theta is maximum angle and minimum angle is pi. Here pi and theta refers to the direction of the secondary waves and initial direction of the light. Here the interference maxima and minima, let us consider the secondary waves traveling in direction inclined at an angle L with the initial direction. It is already shown in the figure. So this is how intensity distribution between throughout the spectrum. From this figure, angle CAN sin theta Cn by A plus B equals Cn divided by A plus B Cn, the equal to A plus B sin theta. Then part difference is equal to add multiples of lambda by 2. Theta is the direction of minima due to interference of the secondary waves from the slits. Then substitute n equals 1, 2, 3, theta 1, theta 2, theta 3 be the corresponding directions of the maxima. Similarly, you can write sin theta 1 equals 3 lambda divided by 2 of A plus B, theta sin theta 2 equals 5 lambda divided by 2 of A plus B sin theta. Then take the difference between sin theta 2 minus theta 1 equals lambda divided by A plus B. From this expression, lambda by A plus B is the angular separation is inversely proportional to the A plus B and the distance between two slits. That is, angular separation between two consecutive maxima or minima is angular separation is inversely proportional to A plus B. From next condition is the diffraction maxima and minimum. Here also let us consider the secondary waves traveling in a direction inclined at an angle pi with the initial direction of the incident light. If the path difference Bm is equal to lambda, the wavelength of the light used, the path difference between secondary waves emit estimates of slits A and B equal to lambda. Here also the path difference between two corresponding points of halves, that is equal to lambda by 2. Similarly, for the same direction of the secondary waves, the wavefront incident on the light CD is equal to 0. Then A plus B sin pi n equals n lambda. Then here also n equals 1, 2, 3, pi 1, pi 2, pi 3 values of the corresponding to the direction of diffraction minima can be calculated. Then last one is intensity distribution due to Fraunhofer diffraction at two parallel slits is shown in the figure. This pattern consists of diffraction maxima and minima and equally spaced interference maxima and minima. The full-time wave, that is largely it is equally spaced interference maxima and minima. In the central region correspond to the central maxima of the single slit diffraction pattern. The intensity of the central interference maximum is 4 times the intensity of the central maximum of the single slit experiment compared to double slit. The intensity of other interference maxima on the two sides of the central maximum, it is gradually decreases. Then from the intensity distribution which correspond to 2A equals B, where A is the width of the each slit, B is the spacing between two slits. Then these two values are independent values of interference maxima and minima. The following multiple choice questions from this topic is, this is refers to the figure above. This pattern is observed which experiment, that is double slit Fraunhofer diffraction. If the separation between the two slits is in double slit Fraunhofer diffraction is changed, what will be observed during the diffraction pattern? There is no any change in the pattern or diffraction pattern observed from double slit Fraunhofer diffraction. Then what is the effective distance between the source of light and screen in Fraunhofer diffraction? That is, we know that there are two types, Fresnel and Fraunhofer. Fresnel diffraction is a source of light and image are at finite distance. In case of Fraunhofer diffraction at double slit, and it is infinite distance from the source. Then conclusion of this session is, Fraunhofer diffraction at double slit experiment, interference maxima and minima condition, diffraction maxima and minima, and how intensity is distributed throughout the slits, that is double slit Fraunhofer double slit experiment. Thank you.